Maayong buntag sa tanan, magandang umaga po sa lahat ng participants. Thank you for attending this webinar hosted by ASEP. Although there was a limited time to prepare when I learned that I'm one of the speakers in today's webinar, I still accepted the invitation because it is such an honor for me to be invited to share my knowledge and experience in steel design. Today, we will be talking about the introduction to pre-qualified welded joints or connections. These are the topics we will discuss for this lecture. First, we will go over some welding-related codes and standards. Second, we will talk a little bit about the basic weld symbols. Third, we will discuss some commonly pre-qualified welded joints. And lastly, we will go over some basic seismic requirements. Let's start our discussion by looking into some of the welding-related codes and standards. In the Philippines, similar to the United States, a number of welding-related codes and specifications govern the design, fabrication, erection, and inspection of welded steel structures. Shown on this slide are the AWS standards that typically focus on welding issues. AWS D1.1, the left image, is a comprehensive welding code governing the design of connections, including connection details, welding procedures, acceptable base metals, filler metals and welding joint details, fabrication and erection requirements, and welder qualification requirements. AWS D1.8, the right image, contains the additional provisions intended to be applied to joints or members that are designed to resist yield level stresses or strains during design earthquakes. Note that in this standard, it is assumed that the structure has been designed in accordance with the ASC seismic provisions. For steel building construction, the primary standard is the ASC specification, shown on the left image. The ASC specification contains a variety of welding-related requirements like details of groove welds, details of fillet welds, and strength of welded joints. In addition, and importantly, Section J2 of the specification, that's equivalent to Section 510.2 of our NSCP, invokes all the provisions of AWS D1.1 except as noted in the specification. The ASC seismic provisions, shown on the right image, was developed to augment the ASC specification, adding provisions deemed necessary for high seismic applications, which require capability to dissipate energy through controlled and elastic deformations in major seismic events. AISC Steel Manual, the left image, contains design considerations for welds. It can be found in Part 8 of the manual, including some design tables. ASC Design Manual for Seismic contains design examples for different lateral framing systems and its connections. Other references for welded connections are the ASC Design Guide 21, the left image, which is written by one of the welding experts in the US by the name of Dwayne Miller. ASC 358 2016 version, the right image, contains design procedures for pre-qualified moment connections. And 2 months ago, I gave a lecture in both ASEP and PICE hosted webinars about some of the commonly used pre-qualified moment connections. And of course, we have the NSCP 2015 and the ASEP Steel Handbook that was published in 2004. Let's have a quick look into some of the basic weld symbols to be familiar with it. Welding symbols, or sometimes called weld callouts, are miniature schematic representations of weld types to be made. These are used as a systematic means of communication to identify welding-related information in a graphical manner. Table 8-2 of the steel manual shows the basic weld symbol, where commonly used symbols are the fillet weld, bevel groove weld, flare bevel groove weld, the backing bar, field weld symbol, and the weld all around symbol. Both here in the Philippines and in the US, weld all around symbol is a commonly misused portion of the welding symbol. Here's a standard format for weld callouts. It includes, at a minimum, a reference line and an arrow. A tail may be added opposite to the arrow end as an option to indicate any specification, processes, or notes. The arrow should point to the joint. The weld symbol designates the type of the weld. It could be fillet weld, PJP, or a CJP weld. For weld symbols above the reference line means that the weld is to be applied to the side opposite of the one to which the arrow points. Conversely, weld symbols below the reference line refer to the arrow side. Note that reading welding symbols is from right to left. Now, a common error is to create a welding symbol with the assumption that the direction of reading is from arrow to the tail, but symbols are always properly created to be read from right to left. For the next part of this lecture, let's try to identify some commonly used pre-qualified welded joint. AISC defines a number of pre-qualified joints that can be made. But before a welded joint can be made on a project, it must be proven that the weld can be made using the desired materials and attain the required strength and ductility. Once the joint has been proven, a welding procedure that details how the weld is to be made is published, and the procedure is considered to be pre-qualified. If the engineer specifies a joint or a weld that has not been pre-qualified, it is necessary for the welders to go through the qualification process to develop a new qualified welding procedure. Listed here are some commonly used pre-qualified welded joints, and we have the fillet weld, the CJP weld, and the PJP groove weld. Let's begin with the extensively used weld, the fillet weld, in a steel fabrication and often used to join shear tabs to columns, gussets to beams and columns, stiffeners to webs, and light columns to base plates, as well as many other examples. As you can see in the images shown, fillet welds have a triangular cross-section and are applied to the surface or edges of the materials. Fillet welds do not fully fuse the cross-sectional areas of the base metal, but it is possible to develop the full strength of the connections. The size of a fillet weld is specified in terms of the leg size, even though the strength of the weld is theoretically controlled by the size of the throat. AISC Specification Table J2.4, also found in Table 510.2.4 in NSCP, specifies minimum weld sizes that are a function of plate thickness based on the thinner base metal. These are used to address welding-related concerns that involve fusion and cracking and not design-related requirements. To make a good arc weld, a minimum amount of thermal energy must be introduced into the joint. Failure to do so may result in the deposition of weld metal without fusion to the base metal. Otherwise, when insufficient thermal energy is delivered to the joint, the cooling rate experienced by the weld and the heat-affected zone may cause some cracking into the connection. Both the ASC and AWS specify the maximum fillet weld sizes as shown on the left image. For a base metal less than a 1/4 inch thick, fillet welds should not exceed thickness of the steel plate. For base metal with thickness of a quarter inch or more, fillet welds should not exceed the thickness of the steel plate minus 1/16 of an inch, or that's approximately 2 mm. These provisions are frequently misunderstood and misapplied. Now, similar to the images on the right for lap joints and some corner joints, it's applicable only to the situation where the welds are applied along the edges. The main reason for these provisions is due to the possibility for welders to melt away the top edge of the member when welding on an edge, as shown on the lower right image. This could result to an effective weld throat smaller than the designer intended. AISC requires that fillet weld lengths be at least 4 times the leg size. This provision, combined with the minimum fillet weld size, results in the minimum weld length requirements as a function of the thickness of the material being joined. In lap joints, the minimum amount of lap shall be 5 times the thickness of the thinner part, but not less than 1 inch or 25 mm. By providing this, the resulting rotation of the joint when pulled will not be excessive, as shown in the left images, where the condition shown in the right-hand image subjects the fillet weld to torsion. Now, for longitudinal welds in a lap joint, the rightmost image, the common practice is to use a weld length equal or greater than the width of the plate. AISC limits the maximum effective length of fillet welds under a specific set of conditions. Consider a lap joint with longitudinal fillet welds. When a tensile load is applied, the fillet welds may be considered end loaded. Now, the maximum length provision permits the weld lengths of up to 100 times the leg size without any adjustments. For welds that exceed this limit, the effective length must be reduced to account for shear lag effects. And for weld lengths exceeding this limit, we have to reduce the effective length using the reduction factor beta, as shown in this slide. And for weld length that is greater than 300 times the leg size, the beta is limited only up to 0.6. In theory, a flat-faced or convex-faced equal leg fillet weld in a 90-degree T-joint has a throat dimension of 0.707 W, where W is the leg size shown on the left image. This assumes that fusion is achieved to the root of the joint, but not beyond that point. If a depth of penetration beyond the root is achieved, the effective throat dimension is increased for fillet welds with equal leg sizes. Now, the effective throat dimension shown in the right image is equal to the theoretical throat plus some additional value due to penetration. Hence, if penetration beyond the root is achieved, the leg size can be reduced and the same weld strength can be achieved. As a result, this can reduce the welding costs. Traditionally, fillet welds are designed to resist the load to the weld's throat, regardless of the direction of loading. Experience and experimentation, however, have shown that fillet welds loaded perpendicular to their axis is approximately 50% stronger than the same weld loaded parallel to its axis. When the direction of loading is considered in design, smaller fillet welds may be possible, resulting in better design economy. However, along with the increase in strength of transverse welds, there is a decrease in the deformation capacity before failure, as shown in the graph. If significant post-yielding deformation capacity is desired, longitudinal weld is preferred. Now, when combining longitudinal and transverse welds into a weld group, the difference in deformation capacity between the two does not permit the full strength of both welds to be achieved simultaneously. With that, the two welds must be strained in a compatible manner. Now, the ASC specification addresses this issue by permitting the use of the greater of the two equations shown in this slide. Fillet weld terminations in most cases do not affect the strength or serviceability of the connections, but in some cases, the disposition of welds affect the function of the connection, and notches may affect the strength and the resistance to crack initiation for cyclic loads. Now, AISC specification permits fillet welds to either extend to the end of the piece or to be stopped short approximately one weld size, except for some specific conditions where additional requirements apply. Common practice is to stop the fillet welds short of the length of the joint. This has a simple, practical reason, and that is carrying the weld out of the full length of the joint increases the possibility of undercut and other weld quality problems. For one typical example, the lap joint between the T-cord and the web members of a truss, the weld should not extend to the edge of the T-stem as shown in this image. A second special condition involves attachments where flexibility is expected, as is the case with the simple clip angle connections as shown in this slide. ASC requires that when end returns are used, they should not exceed 4 times the weld size, nor half the width of the part. This permits the unwelded portion of the member to flex, and end returns are typically supplied for this situation to preclude straining about the weld root of the fillet weld. The final example cited in the ASC specification wherein welds must be terminated short is in the case of welds on opposite sides of a common plane, as shown in this slide. A reason for such interruption is again the workmanship issue. Melting away of the edges is highly likely. Furthermore, the short welds on the edges must be made out of position, and changes in welding procedure parameters will likely be required for the short welds. Another commonly used pre-qualified weld is the complete joint penetration or CJP groove welds. The throat dimension of a CJP weld, by definition, is equal to the thickness of the plates that connected, as shown in this image. So essentially, CJP welds develop the full strength of the attached elements for statically loaded structures. For most connections, CJP weld requires steel backing if made from one side and back gouging if made from both sides as per AWS. This is done to ensure complete fusion of the entire thickness of the element being joined. Now, CJP has some advantages over other weld types. These advantages have also resulted in a widespread of use with respect to the tendency to specify CJPs in situations where there are better options. Let's talk about backing in CJP welds. Backing is an auxiliary piece of material that is used to support and retain molten weld metal, as shown on this image. Although typically it is made of steel, backing may be made of other materials such as copper or a ceramic material. Backing is considered either fusible or non-fusible, depending on whether or not the weld is intended to bond to the backing bar. Again, backing is typically associated with CJP welds made from one side of the plate or the element. When applying CJP welds, preparations are necessary because, except for the thinnest of materials, the penetration of the welding processes is typically not adequate to obtain the depth of fusion required for the needed weld strength. Thinner sections up to a maximum of 3/8 inch may be joined with square-edged preparations using pre-qualified welding procedure specifications, or the so-called WPS. A selection of groove weld preparations are possible for CJP welds. Now, as shown in this image, preparation can be made of square, beveled groove, V groove, J groove, or a U groove. Before we proceed with the succeeding slides, let's be familiar first with the different welding positions. As shown in this image, there are 4 welding positions considered in AWS or AISC. We have a flat position, a horizontal position, vertical, and an overhead position. Table 8-2 of Steel Manual, also found in AWS D1.1, gives a number of pre-qualified CJP welded joint details. The tables provide joint geometries such as root openings, angles, and clearances that will permit the deposition of a sound weld material. As you can see in this image, the root opening for a CJP weld with a joint designation of B-U4A using a shielded metal arc welding is a 1/4 inch and 3/8 inch for groove angles 45 degrees and 30 degrees respectively. The base thickness or the base metal thickness is unlimited and all the welding positions are allowed. Here is another CJP joint detail example given in table 8-2. As you can see, the root opening for CJP weld with a joint designation of B-L2A-S using a submerged arc welding is a 1/4 inch for groove angle of 30 degrees. The base metal thickness is limited to 2 inches max, and welding positions allowed is only for a flat position. Here is another CJP joint detail that is commonly used for directly welded flange of beam to column moment connection. As you can see in this image, the root opening for a CJP weld with a joint designation of TC-U4A using a shielded metal arc welding is a 1/4 inch and 3/8 inch for groove angles 45 degrees and 30 degrees respectively. The base metal is unlimited and all the welding positions are allowed for the 45-degree groove angle. But for the 30-degree angle, horizontal welding position is not allowed. This detail shows the typical weld call-out used for a CJP welded beam to column connection. When using CJP welds, the engineer is only required to specify CJP in the design drawings, in the tail of the welding symbol. This practice allows the contractor to select the type of groove weld, either bevel, V, U, or the J groove, as well as the specific dimensions. This complete information shall be included in the shop drawings, which is typically the scope of the contractor. If a welding symbol without dimensions and without CJP in the tail, according to AWS D1.1, it designates a weld that will develop the adjacent base metal in tension and in shear. Now, this permits the connection detailer to select among the CJPs, PJPs, fillet welds, or a combination of the welds to satisfy the requirements. The last commonly used pre-qualified weld we will discuss today is the partial joint penetration or PJP groove welds. A PJP weld, by definition, has a throat dimension less than the thickness of the elements being connected, as can be shown in these images. The effective throat dimension in PJP weld delineates between the depth of groove preparation and the probable depth of fusion that will be achieved. When submerged arc welding is used and the weld groove included angle is 60 degrees, as you can see in the upper right image, Table J2.1 of ASC specification, also in Table 510.2.1 of NSCP, allows the engineer to rely on the full depth of joint preparation to be used for delivering the required float dimension. When processes with reduced penetration capability are used, such as the shielded metal arc welding, or when the groove angle is restricted to 45 degrees, see the upper left image, it is unlikely that fusion to the root of the joint will be obtained. Because of this, Table J2.1 of AISC assumes that a 1/8 inch of the PJP weld joint will not be fused. Therefore, for such conditions, the effective throat is assumed to be 1/8 inch less than the depth of the preparation. Table J2.3 and ASC specification, also in Table 510.2.3 of NSCP, prescribes a minimum effective throat size for PJP welds. It is a function of the thickness of the thinner parts joint. This table is not based on assumed minimum design loads, but rather deals with welding related concerns. Under the root of the PJP, there will always be an unfused plane because PJP welds do not fully fuse the cross-section of the joint. As a result, performance of the connection is affected because the unfused plane may create a stress concentration depending on the loading direction. When loaded in shear, this stress concentration is of no concern. However, when the element is subjected to cyclic tensile loading, this region must be considered in the design of the connection. Table 8-2 of the Steel Manual gives a number of pre-qualified PJP welded joint details. The table provides joint geometries such as root openings, angles, and clearances that will permit the deposition of sound weld metal. As you can see in this image, for a PJP weld with a joint designation of BC-P2 using shielded metal arc welding, no root opening required, but the root face shall be 1/32 inch minimum with a groove angle of 60 degrees. The base metal thickness T1 is a 1/4 inch minimum, but T2 is unlimited. Now all welding positions are allowed and the effective weld size is the same with the groove size. Here is another PJP joint detail example given in Table 8-2. As you can see in this image, for a PJP weld with a joint designation of TC-P4-S using submerged arc welding, no root opening required, but root face shall be a 1/4 inch minimum with groove angle of 60 degrees. The base metal thickness T1 is 7/16 inch minimum, but the T2 thickness is unlimited. Take note that only flat welding position is allowed, and the effective weld size is the same with the groove size. For a PJP weld, the engineer is only required to specify the effective throat dimension in the design drawings. This practice allows the contractor to select the required depth of preparation, the S dimension, that is appropriate for the welding conditions, process, and position of welding, as well as selecting the type of PJP groove weld detail, like the V, bevel, J, or the U groove. This complete information shall be included in the shop drawings, which is typically the scope of the contractor. Note that E, or the effective throat size, should be shown inside a parenthesis, similar to the red clouded call-out in the image shown. Based on my experience, the most common error in PJP is to omit the effective throat size E from the design drawings. For our last topic, let's talk about some basic seismic requirements in welded joint. Now, after the Northridge earthquake, brittle fractures were discovered in steel buildings. These fractures generally initiated near the CJP weld of the lower beam flange to the column flange. Now, the picture shows a fracture on the beam flange at CJP groove weld of the beam flange to column flange. Note that these fractures are similar to the observed fractures in Japan after the 1995 Kobe earthquake. In the succeeding slides, general welding related issues and factors to be considered for high seismic construction will be discussed. The first seismic requirement for CJP welded SMF connection is the steel weld backing. The use of backing bars in a directly welded flange beam to column moment connection may create notch effects in the weld root, depending on the joint type and the loading conditions. At the bottom flange connection, in particular, lateral forces will cause bending moments, which impose tensile stresses on the connections. The notch-like condition created by the left-in-place backing in T-joints can serve as a stress concentrator and crack initiator as shown in the two images. To eliminate the stress raiser condition as shown in the previous slide, the process depicted in these two images can be performed. First, remove the steel backing bar. Second, gouge the root of the weld, that's the underside of the flange, to sound metal. And third, add reinforcing fillet weld at the underside of the flange. Note that this is an expensive operation that is typically applied only to the bottom flange connection in special moment frames or SMF. For top beam flange welded connection, a simple reinforcing fillet weld added between the backing bar and the column sufficiently reduces the stress concentration. This permits the steel backing to remain in place. See the leftmost image. As shown on the rightmost image, the reinforcing fillet welds should not be placed between the backing and the beam flange because this increases the amount of stress transferred into the backing bar and increases the notch effect of the unfused backing bar. This creates undesirable stress concentrations in the connections. The second seismic requirement for CJP welded SMF connections is the weld access hole, or commonly called as the rat hole. For special moment frames in high seismic applications, the distribution of stresses through the end of beam into the connection is affected by the size and the nature of the weld access hole. Now, the ASE Prequalified Connection Standard, or ASE 358, has special requirements for weld access holes geometries in some situations. In addition, weld access holes are required to be fabricated free of unacceptable notches and gouges that may serve as stress concentrators. Specific workmanship standards for weld access holes are given in AWS D1.8. Shown here is a pre-qualified dimensioning of the weld access holes for directly welded connection using CJP welds. The third seismic requirements for CJP welded SMF connections is the filler metal properties. AWS D1.8 requires that all seismic force resisting system welds are to be made with filler metals classified using AWS A5 standards that achieve the following mechanical properties. So for typically used A70 electrode, the Sharpie V-notch or CVN toughness of the filler metal should be at least 20 pound-foot at 0 degree Fahrenheit. That's approximately minus 18 degree Celsius. The last seismic requirement we will discuss for CJP welded SMF connections is the mechanical properties for demand critical welds. In addition to the filler metal requirements, AWSD 1.8 requires, unless otherwise exempted when testing, that all demand critical welds are to be made with filler metals receiving heat input envelope testing that achieve the following mechanical in the weld metal. For demand critical welds, the deposited weld metal is required to demonstrate a minimum of Sharpie V-notch or CVN toughness of 40 pound-foot at plus 70 degree Fahrenheit. And this requirement was developed based on loading conditions, connection details, workmanship standards, and the inspection requirements. The slide shows a welded unreinforced flange welded web connection. With this connection, the beam flanges are field welded to the column flange using CJP welds detailed as demand critical. Similar to the beam flanges, the beam web is also CJP welded on the field to the column flange using demand critical welds. The welds on the single plate to beam web and column flange, however, need not be detailed as demand critical. Note that the performance of this connection is highly sensitive to the geometry of the weld access holes. Therefore, specific access hole geometry, as discussed earlier, is required. In summary, practicing structural engineers are expected to be accustomed with the welding related codes and standards. Second, be familiar with the basic weld symbols. Third, be able to identify commonly used pre-qualified welded joints. And lastly, be able to describe basic seismic requirements in welded joints. With that, I would say thank you for listening to my presentation.